Perez. I'm working under Renato Pavanero's advice. And I'm going to talk about some of the results from my master research. And it's about evolutionary topology optimization for compliant mechanism design. This is the summary of the topics that I'm going to introduce. The first is the motivation and general remarks. We're going to talk about a little bit about compliant mechanisms, what they are, and a little applications. The second one is the bidirectional evolutionary topology optimization that we're going to call BESO method. It's the one Felipe was talking about. He worked only with ESO, which was the first approach. The third one will be how to relate these two things, how to use the best method to compliant mechanism design. We will be seeing some numerical results and the conclusions. So we start with the motivation and general remarks. So what is a compliant mechanism? A compliant mechanism, it's a mechanical device that achieves motion through deformation. We're talking about no links, no members, no assembly, not at all. We're talking just one member who do all the work. The source of the motion, the source that produces the motion could be at any kind. Could be a force, could be a could be an electromagnetic force, could be at any kind. Thermal, electrical, what you imagine. We will be working with only mechanical forces. They are very new topic. They're very interesting given the advantages. As I told you, they can be manufactured only by a single layer. They don't require any kind of assembly, no lubrication. They're compact, and they can be used for very high precision and reliability. They can be used when the application needs high precision and reliability. But as always, there is a catch. The design, addresses design, it is a very complex task. So that's our goal. So now that we see what a compliant mechanism is, we're going to see the method that we're going to use. To design compliant mechanisms exist different approaches. There is a ground structure approach, which we'll not talk about, and there is the continuum approach. The continuum approach includes all the optimization methods that are design-based. So what we want is to find a better distribution of materials to achieve our goal. What is our goal? Our goal, given that the compliant mechanism, what we want is to achieve motion. So what we really need is to maximize displacement in any point that we want to. So we're going to talk first about the method. The evolutionary structural optimization method. It's based in a very simple concept. You will have a design domain. You will be divided in elements, and you will be gradually removing those elements, those materials, and you will do it slowly enough to kind of reach certain evolution path until you get to the optimal structure. Here is like the algorithm. We start as we speak the design domain. We divide it in elements. We define the condition, the loading conditions, the boundary conditions. After that, we define the basic parameters. They are related to how much material are we going to take for each iteration, and some things like that. I'm not going to be very specific, but they are related to the method, how it works. Then we carry out a finite element analysis to find the displacement field of the structure. And we start with almost full, normally. We start with a full domain, and we'll see how it behaves. Then we calculate, this is a very important part of the process, we calculate the elemental sensitivity numbers. This means that we're going to analyze how important is the presence of an element in the structure. That's what we call the inefficient material. Those elements that are not very important to the design, so we can remove. So what Felipe was talking about, it was about the ESO method, that it was about only removing material. This method also allows to put material back. So in that way, we kind of allow the structure to evolve, get a little lost, and come back to the evolution path. So it is very important, especially for this kind of applications. Now we calculate the sensitivity. Once we calculate the elemental sensitivities, we know which elements we can kind of we know how elements can leave the design domain. But we have to do one more. We use some other two strategies. We use a filter, and we average the sensitivity numbers. Why? Because there is some difficulties, numerical difficulties, that are associated with this kind of methods. Some of these problems are checkerboard problems. There are one-node connections that we can avoid using these two more steps, additional steps. Once we do all that, we can calculate the volume for the next step. As I told you, you remove material gradually. So each step you need to figure out how much you can take from another step, or how much you will add for the next step, depending on which elements are going to be added, which elements are going to be out. And then we construct a new design. We check if that design matches two conditions: a volume restriction and if the objective function is achieved. I'm going to explain that a little later. Some of the important applications from the best method is what described up here. There's so much more application. I include this because there are, especially the fluid structure interaction, are particularly interesting for compliant mechanism design. So now that we address the method, we're going to talk about how to use it to design compliant mechanisms. So the first thing, as I told you, it is very complex because normally the BESO method is used to minimize compliance. It's kind of the average objective function that we use. But here we need to, as a compliant mechanism, need to maximize displacement in a certain point. It also needs to be stiff enough to hold on to the load, to the restrictions, to the loads that it's put on. So we need both. We need the stiffness and we need flexibility. Those two objective functions are contrary. If you have a flexible structure, it is not stiff enough. So we need to find a way to combine them. The way to combine them is this formulation. It's a multi-criteria formulation that we need to use with two different loading conditions. So it's kind of, we study two different structures that are related, and we put it together in one and only one objective function. The first one is we call mechanism design, which will be accountable for only displacements. So the idea here is to maximize displacement. And we include this value here, Kout. It's like we put a, what is the word? It's like we put a spring at the end. We have one input node, we have an output node. We put the string and the output node to reflect the workpiece restriction. If you want to move it, he will be avoiding that movement. So we'll put that to simulate this behavior. And then we will we will have these important variables. We have the output displacement, the input displacement, and the input force. That will be for the mechanism design. And for the structure design, we will have the same boundary conditions, as you will notice, but we will restrict also the input node. And then we will put a dummy load at the output node, also to simulate the restriction of the workpiece. So there is these two different loading conditions with two objective functions that we will be putting together in only one. That is the problem statement. That will be to maximize GA that is called the geometric advantage, which is basically the ratio between the output displacement and the input displacement. And SA, that will be the compliance of the structure. That is our problem statement. Here we can see which, as I said, GA is the ratio of the two displacements, and this is the expression for the compliance of this structure, as I said. And we will continue with the sensitivity analysis. So the sensitivity analysis is very important because it's the part who determines which element stays and which element should leave the design domain. So the presence or absence of an element will depend on this number. This number can be calculated by derivative the objection function that we already seen before, which will be this expression here. And the idea is to which element has a bigger sensitivity number stays, and the elements with the lowest values can leave the design domain. So now we're going to the numerical results. We'll be using two different, there are very typical examples of compliant mechanisms. We're going to address his design. The first is the case of an inverter. The idea is the initial force will be at the left edge in the middle. There will be the input node, and right here will be the output node. As we can see, the restrictions are in the high and low edges of the right part. And the second one, I put it the whole design domain, but we only include it in the half, because that way we could, if you see the displacement, there are two output displacements. To avoid that problem, we only use the half because it's symmetrical. Because it's symmetrical, so if we only use the half, we don't have that problem. So we did it that way. Right here are some basic parameters. I told you some about them. This determines how much will be retired in the next iteration. This represents how much can be added. This represents, it's about the filter scheme that I told you that it was necessary to avoid those numerical problems and things like that. We're talking about the first case, who was the inverter. And this was the results I found. We can see here the convergence. First we have the objective function convergence. The idea was to maximize. So we can see that effectively the algorithm did it. It maximized the objective function, which finally end up maximizing the output displacement. And we see the evolution of the volume of the structure. We depart with a full design domain. If we started here, will be all black. And he removes. This is very interesting, this zone here, because it did things we didn't expect. And that was important that it was BESO that we were using and not ESO, because in ESO, there's some parts here that, parts of material that once what's removed, it cannot go back. And in this case, he kind of meshes until turns to the evolution path. So it was very important that it was BESO and not ESO. And we finally obtained this design. This is a compliant mechanisms with 20% of the final volume, of the initial volume. Now we have some results from the literature. This is our formulation work. How you can see it's very similar. I didn't include the conversions, but it was very similar too. So the algorithm implemented, it was successful. And we also include the deformed topology to actually seeing that it behaves the way it needs to behave. And the displacement at the output, at the output node, it's maximized and the desired direction. We have the second, we have the evolution. It didn't behave that well, but at least the output displacement, it is higher than the initial value. And we only have the half. We can see the evolution, how it also suffers those dramatic changes before he arranges to the evolution path. And we have the comparisons with the results we find in the literature. Once again, if you wanted to see, the idea was to pull in this direction and he closes. And he does that. So it was successful. Now we studied some of the parameters, especially the workpiece restriction to see how it behaves. We didn't find some significant changes. As we can see, this is the maximum value that we could achieve until it kind of breaks. It cannot hold anymore that kind of force. But we didn't find it that the changes were very significant. I think especially because we do include this restriction. If we didn't include it, it will be, the influence of crowd will be much higher. But if we didn't include it, the optimization within work, we will obtain only disconnected topologies. We did the same study for the second case. The results were a little different. It showed more influence, but not quite. It is different. It is even more it is more influential than the first one, but in general, the topology didn't change that much. And we needed to increase the value very high to see any difference. We also study the mesh dependency of the algorithm. We find successful results because we didn't see any difference at any mesh size, which was very important. And we finally get the conclusions. The general concepts of Bezo method were addressed, and the results were successful. The results match the topologies that we already found in the literature, not only for the Bezo method, but only for other optimization methods. The presence of the two objective functions is very important. Otherwise, it will not converge. If we only consider the displacement, we wouldn't obtain these results. We didn't find that the workpiece restriction was particularly influential in the design, and it didn't depend on the mesh size. It didn't vary at all, which was very important. The acknowledgements for the CAPES and FAPESP, and thank you very much.
Questions?
For the virtual case, when you show the change in the convergence of the curve, do you know what happens in the point 80? I guess that is the number when the curve goes down and then.
Okay. Here?
Because maybe I don't know. I that graphic, I understand that the changes that occur in that point, it will be so important for the material that you are designing.
Really, what happens is this bar disappears. What happens here is that it's right at the moment that bar disappears. And between iterations is a very huge change, but it needed to happen, so it kind of rapidly recovers.
But at the end, the final structure, you don't have that bar. Because the method you could delete and put again some parts of your
yes. Yes, but I'm going to explain it here. It depends also in the final volume. These are the structures. This is the structure for 20% final volume, and this is the structure for 40%. So if we saw the graphic for 40%, we will see that he didn't get to this point. He will get only through here. Right here, he does that because he needs to accomplish that final volume. And to do that, he needs to kind of rid of this bar. This is that significant change. If he did it only through here, he will do this. It's the same here. If you see, this is those bars. All of this are significant changes in the topology. All of them. It's because from one iteration to another, the topology changed so radically that, for example, the compliance will be totally different. So the objection function changes also.
But at the end, the program can stabilize the structure also without that part. So this is why it will happen in the normal.
Please, would you mind going back to the slides where you, yeah, that one, where you present, no, the next one, yeah, case one and case two.
Okay.
So case two would be what you call the gripper, is that?
It's the stiff of the string.
Okay. Case two has a string with different stiffness.
Yes, it's the stiffness of the string. How much the string it is, it will be. It's kind of a equivalence for force, but it's an easy way to put it in the algorithm.
Okay, sorry, but why do you have two different drawings? I missed. Sorry, what is case one and case two?
Which one? I don't know.
No, you have different drawings.
I have case one and case two. The case one is an inverter, and the case two is a gripper.
Okay, thank you. So, what should an inverter and a gripper do in a mechanical system? Sorry for
They're actuators. I don't know.
So no, but an inverter, you said, when you have a force that way?
It's because he needs to invert the direction. The algorithm needs, when you start the optimization process, both the initial field displacement will be that the displacements at this point will be in this direction.
Okay.
So he needs to accomplish the other. He needs to, we pull on this side, and he goes through another. That's what is called inverter.
This kind of mechanism is normally used for a small size, micro mechanism.
Like box, what?
Like to manipulate cells or in microscope.
Okay.
Things like that. Because the displacement is very small and the force is also not too large.
Yes.
For this kind of application. They did that with additive manufacturing process. Normally for the small force and small space.
Okay. So the inverter inverts the direction of the force applied?
Yes, and
the gripper
catch something and
it's like a piece.
yes, exactly.
Okay. Thank you.
All right. Thank you very much, Claudia.